In this segment, we discuss what light is. In short here, what we have is what we call the electromagnetic spectrum. Electromagnetic spectrum, let me write it down here. Electromagnetic spectrum. The electromagnetic spectrum is a vast spectrum encompassing lots of waves that share the same properties. Now, waves including what we call radio waves, like what you see here, microwaves, infrared, visible light. This is actually what we call light, the visible part of the spectrum. Ultraviolet, X-rays, and gamma rays. All of these are part of the electromagnetic spectrum. Light is what we consider the visible portion of that. Now, when we talk about wavelength of these different types of waves, radio waves have a wavelength from 10 to the 4 to 10 to the 2 centimeters. 10 to the 2 centimeters is about 1 meter, about 1 yard, to about 100 meters. That's the radio waves. Microwaves are more in the range of 1 centimeter. If you look again at your microwave oven right now, when you turn it on, there are 2 waves involved when the microwave oven is working. The visible light wave and the microwave that's heating your food. Now, as you notice from your door, the light wave is going to be able to exit the door, exit the mesh of the door, allowing you to see what's inside. However, that mesh that's part of the door of the microwave is smaller, slightly smaller than 1 centimeter, preventing the microwaves from exiting. Infrared is actually what we consider as heat. That's whenever you go to a fast food place, what keeps your hamburgers or fries or whatever warm is those infrared lamps above them. And it is more 10 to the minus 2 centimeters. So about 1/100th of a centimeter. Now, visible light, the wavelength is much smaller, 10 to the minus 5 centimeters. And so on. When we go all the way to gamma rays, it's 10 to the minus 12 centimeters. You notice it's quite a range of wavelengths. Now, we have here these images showing us what the size of these wavelengths compare to. We talk about the size of buildings all the way to the size of atomic nuclei. Again, this is a picture of the same electromagnetic spectrum. One note here, we have all of this is represented in terms of wavelengths. An alternative way of representing it would have been in terms of frequencies, and we'll get to that a little later. Now, what makes an electromagnetic wave or a light wave as part of the electromagnetic waves? It's actually, and we'll learn it when we discuss this later on in the course, all what you need to have charges moving up and down along a conductor, like this one here, an antenna. And as the charges move up and down, accelerate up and down that conductor, they are going to generate an electrical field that's going to be in the up-down direction. And that electrical field disturbance is what's going to travel, resulting in what we call the electromagnetic wave. Associated with that with that electrical field that we just talked about up and down, there will be a magnetic field perpendicular to the electrical field. That's why we call it electromagnetic wave, because it is a combination of both an electric field and magnetic field that are perpendicular to each other, and both of them oscillating at the same time at perpendicular directions and perpendicular to the direction of motion of the wave. One thing worth pointing here, if you remember, when you talked about waves, you talked about transverse waves and longitudinal waves. This kind of wave is a transverse wave since the oscillation is actually perpendicular to the direction of travel of the wave. But the oscillation here is the oscillation of both the electrical field and the magnetic field. Also, one thing you would like to note, a crest in the electrical field corresponds to a crest in the magnetic field and vice versa. Okay, so that's what makes it an electromagnetic wave. As I just mentioned, it is a transverse wave. The electrical field and magnetic field are in phase. They increase and decrease at the same time. A crest corresponds to a crest and a trough corresponds to a trough. Now, what's different from sound waves, what's special about all electromagnetic waves is they can travel in empty space. We are thankful to that. Without that, we would not exist. We get the sunlight, that's the origin of all the energy that we live off. It's coming from the sun to us through empty space. All electromagnetic waves travel in empty space. Now, the speed of electromagnetic waves, this is applicable to all electromagnetic waves, including visible light. The speed of light in vacuum empty space is given by this in SI unit, 3×10⁸ meters per second, approximately equal to that, or 186,000 miles per second. We'll talk later on about this when we talk about electricity and magnetism. We'll see actually it's given in terms of these two other constants that we'll use when we talk about electricity and magnetism. But usually for the speed of electromagnetic waves, instead of using V, we use the symbol C. C refers to the speed of light in vacuum. When light is going to move in another medium where its speed is less than C, we still use the V. Now the frequency is going to be related to the wavelength, the same equation that we discussed before, but in this case, in vacuum, it's going to be C over lambda. Now, as a small example here, we have an electrical field of an electromagnetic wave that is broadcast at this frequency, and this is traveling to the right. First question is, what is the direction of the magnetic field? Okay, that's an easy answer. Our wave is traveling to the right. That's the direction of travel. The electrical field is up and down. The magnetic field is always perpendicular to the electric field. So this is the way the magnetic field is going to oscillate. Now, let me remove that. Then the next question, label the two tick marks on the x-axis. So what are the tick marks? Here are the tick marks. So it's a wavelength. Okay, here from here to here we have a wavelength and another wavelength. We have the frequency. Frequency is C over lambda. Now we are trying to find lambda. So lambda is equal to C over F, which is 3×10⁸ meters per second over 96.1 megahertz. Mega is a million, so 10⁶ hertz. So my lambda is actually equal to 3×10⁸ over 96 10 to the 6 meters. So it's going to be 100 over 32 meters. That's equal 3.125 meters. So this is going to be 3.125, and the other one, it's going to be, we add another period, so that's that number times 2, which is 6.25 meters. Remember, for light, like for any other wave, we still have these equations. The only difference, remember, in vacuum, this is going to be C instead of V. Okay. Now, as light travels in vacuum, the speed is given by this. Or 310 to the 8 meters per second. Now, if it moves in another medium, its velocity or its speed in that medium is going to be given by this equation. V is going to be the speed of light in vacuum, C, over n, what we define as the index of refraction of the medium. Now, the speed of light in vacuum is the highest speed that light can move with, meaning that all V's are going to be smaller than C. They cannot be larger than C. That's, if you take a little modern physics, that's the basis of relativity. Now, because of that, that means the index of refraction is always larger than 1. The index of refraction for vacuum is then 1. Index of refraction for air is approximately equal to 1. Index of refraction of water is about 1.3. Index of refraction of most glass is about 1.5, and so on. Now, when we have media like this, what this tells me, when I go from a large wavelength to a smaller wavelength, that tells me high speed to lower speed. Lower speed means higher index of refraction. If I have here N1, N2, that means N2 is larger than N1. And here, when I have a large wavelength, and then, when I have a small wavelength and I go to a larger wavelength, that means that the wave here is moving faster. That means that the index of refraction is smaller. Okay, that's the end of this segment.